Hello, I'm Toby O'Geen. I'm a professor and soil resource specialist in cooperative extension, and today I'm going to talk to you about the fate and transport of sediment in California rangelands. Erosion is an incredibly important process to understand in our landscapes. It influences the productivity of our land, it influences water quality of our land, and because it influences the productivity of our land, it also influences biodiversity in our land. And so I'd like to start by introducing you to the simple mechanisms of soil erosion. These mechanisms are very simple in that it is driven by raindrop impact. There's a tremendous amount of force that is captured in a raindrop falling from the skies. And when that raindrop hits the soil surface, it has a lot of power to it, and it can disrupt the aggregates of soil. When it hits an aggregate, it essentially destroys it if it's not protected by vegetation. And that aggregate then falls apart. The clay, the silt, and the sand, which comprises that aggregate, is now free and unassociated as individual particles. So detachment by raindrop impact is the first step in that process. And as particles are detached from one another, they are then available for transport by surface runoff. Ultimately, that surface runoff is going to stop somewhere. In many cases, deposition is the last part of erosion, in that as the energy of the surface runoff changes, meaning that as it hits a lower slope angle, that sediment load within the surface runoff will be deposited. And so it starts with detachment by raindrops, facilitated by transport of sediment as surface runoff or overland flow, and then ends as deposition of that material somewhere else in the landscape. So there are three different types of soil erosion that soil scientists consider: sheet, rill, and gully. This slide is showing you sheet and rill erosion. Sheet erosion is really maybe the most prolific or abundant process that goes on. This is thin film or sheets of water that is very subtly moving over the soil surface with no defined channels that are transporting sediment. It's a film of water that is hard to detect and is slowly moving with the slope down the landscape. Rill erosion, which is also a common type of erosion, are small channels that form as sheet water, the water in surface runoff from sheet erosion, starts to coalesce into these microchannels. And these microchannels focus water, creating slightly higher velocity, carrying more sediment load. And so sheet erosion tends to evolve into rill erosion as surface water runoff increases. Sheet and rill are responsible for the most sediment transport via erosion because it's essentially occurring all over the landscape. But the effects of sheet and rill erosion in terms of traffic moving equipment across the landscape are relatively minor. The third type of erosion is gully erosion, and this is a more catastrophic event. Gully erosion isn't necessarily responsible for large sediment volumes when you think of the global perspective, because it's relatively small place-based event, but it has catastrophic events or outcomes in that it limits or it degrades the land so severely that it limits the way in which you can use the land. Equipment can't travel across gullies, cattle can't move across gullies, people have a hard time moving through gullies. And these features cannot be restored. If you fill them up with sediment, bring back all the soil, it will just wash out in the next large rainstorm. It's not something that can be fixed, whereas sheet and rill erosion can be. So just to summarize the mechanism, overland flow detaches and transports particles. Flow exerts a shear stress on the soil surface, which detaches particles from soil. Flow detaches particles by exerting shear stress on the microchannels that are forming in rills. And so as water is focused in the rills, there's more and more velocity, there's more particles in that water, and it essentially degrades and erodes itself, and the rills can grow. Rills can grow into gullies if they're not managed carefully. And so as you focus water in a rill and you get more and more water running through it, the velocity increases, the shear stresses increase, and you get more and more transport. And so it's very important to pay attention to how your landscape is evolving from sheet and rills and ultimately into gullies. So what are the impacts of water erosion? Well, there are off-site and on-site impacts. On-site are probably what we're most familiar with. Severe land degradation can occur with severe erosion. That will reduce the quality of the soil and its capacity to produce vegetation. The quality indicators might be losses of soil organic matter, losses in nutrients, losses in the seed bank, diminished water holding capacity, less topsoil, and therefore maybe some subsoil near the topsoil that is less prone to supporting vegetative life, and a diminished yield and productivity as a result of this. The off-site effects are largely contamination of surface water bodies with sediment, nutrients, maybe pesticides or pathogens, but also deposition, local effects. When sediment is deposited on roads or in water conveyance systems or in reservoirs, that destroys habitat, that destroys water quality, but it also can diminish our water supply or our carrying capacity over time. And this can be very expensive. So this is just a table to show you the implications of removing topsoil. Topsoil is the most productive part of soil. It's where all the organic matter is. It's where a lot of the water holding capacity and nutrients are. And so when we lose that material, we lose the capacity to support plant life. And so this table shows, it's just an experiment where no soil was removed, 5 centimeters of soil was removed, 10 and 20. And it looked at the corn yield reduction in terms of a percentage across these different losses. And it looked at it at 3 different locations. And so with no soil removal, we saw no reduction in yield. With 5 centimeter loss in topsoil, we see a 95% yield reduction at location 1, a 30% yield reduction in region 2, and a 70% corn yield reduction at location 3. And so this has an effect. This has a similar effect with more and more sediment removal. You see more and more yield reduction to the point where it's approaching 100% yield reduction with 20 centimeters of removal. And what you see is that trajectory of yield loss or reduction is different for different locations. And that is largely an effect of the topsoil or the nature of the topsoil and the nature of the subsoil below it. If you have quality subsoil, removing topsoil may not have a big impact on yield. But if you have a poor quality subsoil, like that in location 1, even a little bit of removal can have drastic effects on yield. And so it's how thick that topsoil is and how conducive that subsoil is to plant growth that influences the resilience of that landscape to erosion. And that's the point of this table. And so I'm making this same point with these graphs here. We're seeing that productivity is a function of soil loss and technology and the characteristics of subsoil. And these are just kind of a modeled figure that shows productivity across the y-axis and soil loss across the x-axis. So in areas where we have high technology, we can essentially limit the effects or mask the effects of subsoil loss. If we irrigate or if we fertilize, even if we're losing soil, increasingly losing soil, it has a diminished effect on productivity. But with lower technology, such as that in rangelands or in developing countries, we don't have the capacity of offsetting that soil loss. So the trajectory of increasing soil loss is steeper with its effect on productivity. The slope of these lines is much steeper when you have an unfavorable subsoil. Above, we had a favorable subsoil. Here, a poor quality subsoil. And you can see that even with high technology, you can't fix that soil if you're losing that topsoil. Factors affecting erosion are the infiltration capacity of the soil. So to limit erosion, you want to absorb as much rainfall as possible. And so the greater the infiltration rate of soils, the less capacity there is for surface runoff. The steepness of the slope and the shape of that slope also influences surface runoff. If you have long, steep slopes, they're going to be highly prone to erosion. If you have slopes that are concave and focus water, that's going to put more water in a defined area, a concave region, which then accelerates erosion. Soil cover is very important because it protects against raindrop impact. The intensity of rainfall is really important, and also its duration in influencing surface runoff and erosion. And then also soil characteristics play an important role. So what are those soil characteristics? Well, here are a few. Texture is probably the most important property of soils that relates to soil erosion. Interestingly, our loamy textures, the equal influences of clay, sand, and silt, are most prone to erosion. And that's because the particles that are most readily detached by water runoff are very fine sands and silt particles. And so loamy soils have high concentrations of very fine sands and silts. These particles are not so small that they aggregate, and they're not so big that they're just hard to transport by water. And so that's why they're most prone to erosion. Structure is the aggregation of sand, silt, and clay into larger shapes and sizes of aggregates. And so individual particles that are aggregated together can resist erosion because for two reasons. First, it's a larger particle that is difficult to transport by water. And also, these particles are aggregated kind of weakly by glues that allow them, that protect them from being dislodged by raindrops. Root density plays an important role. It acts like microscopic nets that hold particles together, and it prevents particles from being detached. It also stabilizes aggregates and forms structure. Organic matter, or humus, is the natural glue that holds particles together into aggregates and structure. By creating soil structure, that also increases surface infiltration, which limits erosion. Iron oxides, the reddish-brown, orangish color of soil. This is iron that's released from weathering of soil particles, and that weathering, that iron acts like a glue in soil material and holds particles together, making them larger than their individual sand, silt, and clay particles. Promotes structure. And surface crusts. As a raindrop hits the soil surface, dislodging silt, clay particles that can coat the soil surface, like in this photo here below. These sheets of sediment are slowly permeable to water, and they create almost like highways for surface runoff that can then create greater shear stresses on the soil surface, detaching more particles and creating severe erosion. This photo in the center shows you all these little micro aggregates, these little granules, good soil structure that would have optimum soil infiltration and good resistance to raindrop impact. Here we're seeing the root hair effect of aggregating sand particles together. So the amount of cover, as I mentioned earlier, is really important to maintain in terms of limiting erosion. In general, there is a high degree of cover in annual grass systems in California. And that's just because of the sheer density of seedlings that emerge into grasses in these landscapes. So there's a high amount of cover that offers a natural protection in rangelands across California. But excessive grazing can make these landscapes highly prone to erosion. The process is excessive grazing leads to low cover, and therefore our soil surface is exposed to the forces of a raindrop impact. High grazing also tends to relate to high degree of compaction, which destroys soil structure and allows surface runoff to occur more readily. It decreases the infiltration rate of those soils. All of this combines to create higher runoff, surface runoff, which transports particles across the soil surface. So this is a figure that shows you the significance of cover on a landscape. Here on the y-axis we have soil loss reduction in percent and relative to bare soil, and across the x-axis is cover in percent. And what this graph is showing you is that soil with a 20% cover will have a 50% reduction in soil loss compared to bare soil. If we have 20% cover, that equates to a 50% reduction in soil loss. And so a little bit of cover can go a long way. In many of our annual grass systems, from high to moderate grazing, you'll have upwards of 90% cover, unless it's excessively grazed. So we wanted to evaluate the regionality of soil erosion across annual grass rangelands in California. And to do that, we used the revised universal soil loss equation, which is an erosion model, a simple erosion model across the state. And we were trying to understand how different combinations of topography, soil, climate, and cover influence soil erosion. And we modeled 3 different vegetative states that loosely correspond to scenarios of residual dry matter targets. We assumed a scenario of low cover, less than 600 kilograms per hectare of residual dry matter. We simulated a moderate cover between 600 to 1,100 kilograms per hectare of residual dry matter, and high cover, greater than 1,100 kilograms of residual dry matter per hectare. And so these different cover values are expressed here as a dense hatching, a loose hatching, and a very, very single-lined hatch. Those are the 3 scenarios. And then we ran the model in a GIS, a Geographic Information System, across the state in different soil rangeland management zones. And these rangeland management zones were described based on differences in soil type, climate, topography, and vegetation type. And so we came up with 6 different rangeland management zones based on that regional analysis. And so this graph below shows you the outcome of that experiment. And it shows here erosion potential modeled in tons per acre per year, statewide across the different residual dry matter or cover types, and across different regions in the state, these different soil regions. So the take-home message initially is that erosion modeled by the universal soil loss equation is very low across the state. Statewide, we're less than 0.1 tons per acre per year across any cover type. Just for your own perspective, 5 tons per acre of erosion is equivalent to the thickness of a dime. And so we're much, much lower than that here in this modeled scenario. So very little soil loss is occurring on these landscapes. But over time that can add up. And also there are hot spots that we want to be aware of. We also found that some regions are lower in erosion than others. Here you can see that region 1, 3, and 6 have much lower erosion than regions 2, the statewide, region 4, and 5. And so there are areas that are more prone to erosion, primarily because of differences in climate. Rainfall intensity really plays an important role in this equation. And so areas that have gentle rains and low rainfall are going to be less prone to erosion by water than areas that have more intense rainfall. We also see that the response to cover differs across these regions. For example, in regions 4 and 5, you see a much greater difference between low cover and high cover compared to regions 1, 3, and 3, where that difference between low and high cover is almost non-existent. And so the effect of cover can be very different across the landscape. And that's probably a result of both rainfall intensity and soil type, and possibly even topography. So if you look at that in map form, these are the results of that modeling effort in California under a moderate residual dry matter scenario. And if you look at this from a distance, what you see is wow, erosion is pretty much low throughout the state, as indicated by the green coloration, which is between 0 and 0.2 tons per acre per year. But to some extent, this is an issue of scale. When you zoom in and look at these landscapes a little bit more carefully, here I'm zooming into this square near San Luis Obispo County, you can see that there are, if you look carefully, there are some areas of yellow and orange and even red, indicating 5 to 19 tons per acre per year. So there are hot spots in the landscape that we need to be mindful of. In general, the annual grass rangelands of California are resistant to sheet and rill erosion as modeled by the Russell equation, the universal soil loss equation. But there are parts of any landscape that can be highly erosive, and those could be our very steep landscapes, those could be our loamy soils, or those could be regions where rainfall intensity is quite high. So we do need to be mindful of that. Because we feel, generally speaking, that erosion by sheet and rill in California rangelands is not terribly severe. It's important to focus on specific target areas where erosion and rill and gully erosion can really be a problem. And those areas have been discovered to be trails, roads, and culverts. Trailing by cattle can create pathways devoid of vegetation that can be essentially conduits of sediment moving down across the landscape. A poorly placed culvert that is not protected can create erosion that can turn into a gully quite readily, as shown by this photo here. Also, a poorly constructed road, too steep and not compacted to the right bulk density, can also be severely prone to catastrophic failure, as indicated in this photo. So we can avoid these problems by using professionals to build our roads, by armoring the outputs of culverts to protect and spread that water rather than focusing it and spilling it onto the surface, which can cause detachment of particles and ultimate evolution of that spot into a gully. Also, we can reduce the magnitude of trailing by decreasing the distance between foraging sites and stock water or supplements. We can spread the cattle out rather than concentrating them by keeping them moving with water, properly developed water and supplements to move them across the landscape, therefore diminishing that superhighway effect of cattle moving across one spot from upland to, say, stream over and over, which would create a direct route of erosion, of a pathway of erosion to a surface water body. This figure is just showing you how it compared a grass, a trail, erosion on a trail, to an adjacent grassed area. And it compared the erosion, the sediment loss and surface runoff in 1997, 98, and 1999. And this sediment is in a log format. And so any difference is an order of magnitude difference. So, 1 unit change is a large difference. And so what this graph shows is that trail erosion was significantly higher in 1997 and 98 compared to the adjacent grass. In 1999, it was not, because the rainfall was much more gentle and much less of it. So, as I mentioned, sheet and rill appear to be somewhat low in California rangelands. Gully erosion is a real problem because of the catastrophic nature of it. It tends to form because of poorly constructed roads and or poorly placed culverts, which create a focus point from which erosion can occur, and then they grow into these very massive, large cutouts. There's really no way to fix these events. You can't fill them up. They will just, the material, if you did push all the sediment back into that crevasse, it would just wash out again the following winter. So really they need to be armored and protected once they form with riprap to prevent them from growing. And in this case, to prevent this scenario where they might grow and even encroach the neighbor's property crossing this fence. So you really need to be proactive in stopping these things if you can't prevent them. Tree roots help prevent gully erosion in 2 ways. Trees stabilize and anchor the soil, holding it together, but they also utilize water. So they prevent the supersaturation of these soils. When soils become saturated, they essentially become lubricated, and therefore saturated soil on steep slopes are prone to failure. And so that's what you're seeing in this photo, in this image right here. You're seeing a small landslide that's occurred in this area that was cleared of all its trees. So these trees they may not always prevent this landslide failure, but they can minimize it or help protect from it by that anchoring effect, and also by using water, preventing it from getting too wet. So keeping some density of trees might be effective if your landscapes are steep and your soils often saturate. So thank you for your attention. Remember that even if erosion does not appear severe, over time it can build up. And even if it's the thickness of a dime or less than the thickness of a dime, the process of building topsoil is very, very, very slow. It can take up to 500 years to form an inch of topsoil. So even if it's very minuscule and you see no evidence of it, we want to be mindful that erosion is always occurring and that we don't want to accelerate it with poor management. Thank you.
You can find more informative presentations covering ranch water quality topics on the UC Rangelands website, and look for the Water Quality Information Hub or direct your web browser to the URL shown on this slide.